again. So here's another lesson. It's related to the one we did on Monday. We did exponential growth and decay models for increasing and decreasing situations. This one is more tied to money things, and this should be very applicable because everybody's going to want different types of savings accounts or investment accounts that gets interest. So you're gonna see this used quite a bit in real life. So compound interest, what it is it's interest that's paid on a principal investment and any previously earned interest. So if you deposit money into a savings account or into an investment account or a college fund account of any type, usually there's some sort of interest rate. And so if you just let that money sit there, you're going to get interest on that money. And then the next time you get interest, you'll get interest on the money that you had and also the interest that was already there. So it really compounds. So it's very exponential. And the nice thing is they've created a nice model for you to be able to do that all at once. That way you don't have to figure out your interest every single year. So you can just plug it into the model and it will take all your initial stuff and figure out the interest after so many years. So let's look at that model. It looks kind of big. It is very reminiscent of the growth model that we did on Monday. There is one little thing that changes. So I actually have the stuff typed down below for what it is. There's a couple of different letters. R and T are the same, and then we use A and P. A is used in a slightly different way in this model, but here we go. So A is the final amount, the amount after time, like Y was in our growth and decay models. So that's typically what we're finding. Eventually in sort of upper level situations, sometimes we'll know that and use it to estimate something else in there. But for right now, that's what we're looking for is the A. P stands for the principal amount, which is like your initial investment. Okay, so P is your principal initial investment. So that goes here in front, just like you did before, because what you're going to multiply to it is this compound interest factor. So again, 1 still stands for 100% of the original. I didn't type that up because we talked about that on Monday. So it's still 1% of the original, but what you're adding to it instead of just R is that now there's R and this N. We'll talk about N in a second. R is still the rate, and again, it's still as a decimal. Typically, interest rates are set up per year, but most of the time banks and different investments, they give it to you a little bit more often. So they might give it to you a little bit of interest every month. And so that is what affects our rate. That's what the N is. Also, they might also give it to you monthly, quarterly, different things like that. So N could be a couple of different things. And it actually isn't usually a number in the problem. It's usually some sort of phrase. So N is the number of times compounded per year. So like I said, interest rates typically set up per year, but usually, like I said, instead of just giving you the interest once, they give you the interest periodically throughout that year. So then what they'll say is how many times it's compounded. So like you'll see this word compounded in the problem, and then after it will tell you how much there are. And so here's some common ones. So annually, like typically we don't see this, but every once in a while you work with an account that just gives you once a year. So annually, N would be 1. Semi-annually, if you've ever done a semi-annual sale, that's 2 times a year. Quarterly, this is I'm going to underline this one. That's a big one. A lot of investment accounts do that. Some bank accounts do that. So quarterly is dividing it up into 4 pieces. So that'll be N is 4. The big one that is used most often is monthly. So a lot of times banks will take that interest rate and divide it into 12 chunks. So here will be N equals 12. A lot of regular savings accounts are monthly. And then not very often do you see daily, but for our cases, I know with leap years, and we're actually in one right now, you could do 365.25, but that would be off by less than a penny. So typically for daily, for our estimations, we just use 365. Okay, another one, I would usually talk about this in class, so I don't usually type every single thing, so that's why I put etc. The other one we do quite frequently is weekly in some of our cases, and weekly would be every week, so 52 weeks in a year, so that's another common one. Bi-monthly would be every other month, so instead of 12 would be 6. Bi-weekly would be every other week, so instead of 52 it would be 26. Those are a couple more that you'll see. But I went ahead and added weekly, just because as a typically, there will be, on my problems, I try to give you a variety of them instead of using always quarterly or monthly, which I'll go underline monthly too. So those are the two most common real world ones. But we do look at other situations where instead of those two, it's one of the other 4 I have up there. Okay, so if you notice, that's what is affecting R. It divides the R, because like I said, typically interest rates are a yearly thing, but then they don't give it to you once a year, so they take it and they divide it into chunks. The other thing it affects is if you notice N is used a second time up here in the exponent, it's multiplying your time, because T is still your time. Now, what your exponent is actually how many times you get that interest in that time frame, okay? So it's no longer just the years. So if you are working with something and you look after 3 years and you get interest once a month for 3 years, then your exponent's gonna be 36, because that's how many times you got that interest within that time frame. Because that's what the exponent usually is how many times that you figured in that interest. So if you get it once a month for 3 years, you've gotten that interest 36 times. And so that's what is able to allow us just to plug stuff into the model instead of figuring out every single year, is that if you use your exponent as how many times you got your interest, then the formula does it all for you. So again, a quick review of the parts. So A is your initial or your amount after time. P is the principal amount. 1, still 100% of the original. R is your rate. And again, your rate will be given to you as a percentage, but when you put it into the formula, use it as a decimal. N is used twice. It's how many times it's compounded, which means how many times you get that interest in that time frame. So it divides your rate and it multiplies your time, and then T is your time. And typically this stuff is set up in years. So I'll give you a few seconds to look at the formula. So I'm just gonna do a couple examples. Like I said, it'll be set up similar to our growth and decay models from Monday. I want you to show me all your setup, so that way you can make sure you have all the parts in the right spot. After that, you really don't have to show me step by step. The calculator should be able to do it for you. Again, I would do it piece by piece instead of trying to type it all on once, especially with this, because there's a lot of other working parts with this. And I'll show you one thing that we actually do before we start solving it. But let's go ahead and do an example, get stuff set up, and then we'll talk about the solving. So we're looking at an investment account. It pays 5.4% interest, and it's compounded quarterly. If $4,000 is placed in this account, find the balance after 8 years. Now we're doing it's just basic compound interest, because the formula changes a little bit if you're doing like multiple deposits. So all of our examples are just planning on taking that money, putting it into the account, and then not taking anything out or putting anything in from that. Because like I said, that affects our model a little bit. So we're just doing basic compound interest. So again, all we need is a couple of different parts. So I'm gonna rewrite the formula since it's on my last slide, so that way I can point at some stuff. So it's P, and then 1 plus R over N, and then to the N. Okay, so the A is what we're finding. Our principal is our initial amount, Okay, so our initial investment is at $4,000. So that's going to be our P. And then again, always one. That's just how all types of models work. Because to get the stuff inside the parentheses, it's a growth rate or a decrease rate. So we take 100% of the original and we add on our rate. Like, so we're not just giving the rate once a year. We're giving it multiple times. So we take the rate and we divide it into that many pieces. So our rate is 5.4. And again, we have to move the decimal place twice. So since this one already is an existing decimal, we move it twice. So our rate is going to be 0.054. So that's what our R is. And now we divide it by N. Okay, that gives us our R. N is not a number in the equation, it's actually after a phrase. So whenever you're looking for N, look for that phrase, compounded, and then after it, will tell you how much it is. Compounded quarterly, that means N is 4. So that finishes the inside of our parentheses, and then the exponent is N again. So 4 times our time. Our time would be 8 years. And we have everything set up. So we got our initial investment, 4,000, and then 1 plus the rate divided by the number of times compounded. Again, compounded would be how many times we get that per year. So instead of getting 5.4% interest once a year, we get it 4 times a year, so we divide it up into that many pieces. And then it also multiplies how many times we get it. So you multiply it times 8 years. So we have everything set up. Now, before I start solving anything, the biggest thing that would mess this up if I'm trying to do it in my calculator is the exponent. Because if you try to just type exponent 4 times 8, what the calculator ends up doing is taking it to the 4th power and then take the whole thing times 8, which is wrong. So the first thing I actually do is I multiply this exponent out. So I'm not going to rewrite it, but I am going to cross it off. Because my exponent is 32, okay? Because that's 4 times 8. So that's how many times you get the interest throughout that time frame. So my interest is going to be, or my exponent is going to be that 32. And like I said, the biggest thing that the calculator will mess up is that. So before I do anything else, go ahead and do that multiplication, so that way I know my one exponent, okay? So now let's solve it. So order of operations still tells me parentheses first. In there I actually have 2 things. I have an addition and I have a division. Order of operations then just tells me to do the divide first. So I'm going to take the 0.054, divide it by 4. Now this is going to give me a decimal. Okay, don't worry about estimating that, just leave that in. So once I've divided it, add 1 to that. So that gives me my parentheses. So that's my rate here in the middle. Okay, the next thing order of operations tells me to do is the exponent. So I'm going to use my exponent button right here. Click that, then take 32, hit equals. Now this is going to give you a crazy long decimal. Again, don't worry about estimating that, just leave that in, because that's now my entire compound growth interest rate. And so now I'm going to take that times my initial investment, and that'll give me my total amount after 8 years. So after 8 years, that money just sitting there, it's now up to $6,143.56. About wrote my dollar sign at the end. I don't know why I did that. And one reason I tell you not to round in the middle is because you don't want your banks to round, you want it to be exact. Because sometimes if you round in the middle, then your answers will be thrown off. So if you just leave everything programmed in your calculator, you should be able to type it all in. But like I would suggest doing it in steps, because sometimes calculators aren't so good about using correct order of operations. I want to do one more example. It's all the same stuff, but I like doing a couple examples, so that way you have a couple more points of reference from the notes. The only thing that might be a little bit different with each problem is how much it's compounded. Like I said, the most common ones are going to be quarterly and monthly, so you see that a lot. But we will work with some that have a little bit different ones. So this is another one. We talked about it, but again, I want to show you an example of it. So we're finding the account balance after 20 years. If $1,200 is placed in an account that pays 1.2% interest and compounded semi-annually. Okay. So a couple things to compare this to the last one. For one thing, we're not getting the interest quite as much because we're getting it semi-annually instead of quarterly. The other thing is we had a higher investment to start with, and also we had a higher interest rate. So this one probably won't be as good. It's a little more accurate with what savings accounts are right now, but even then it's 1.2% is a little higher than regular savings accounts. But this will give us another point of reference for compound interest. So my initial investment for this one is $1,200. And then it's 1 plus the rate. So our rate here is 1.2. So inside my formula, it's going to be 0.012. Because you move that decimal place twice. And then we divide it by our number of times compounded. And that's right here, our phrase compounded semi-annually. So semi-annually, N would be 2. Again, semi-annual sale, you get this twice a year. Semi-annually, N would be 2. So we're dividing that into 2. And then we use twice, or 2 again. We take it 2 times our years. Here our years is 20. And we have everything set. The first thing I'm going to do, I'll rewrite this one for those who are just looking at my PDF notes. Oops. Again, the first thing I'm going to do is multiply out that exponent. So it's going to be 40. So this time we are getting the interest more because we're looking at a longer time frame. But we do have a smaller interest rate, and it's we're only getting that interest twice a year. So again, we're going to multiply this out now. So parentheses first. So we divide it first. 0.012 divided by 2. Add 1. So that gives us our parentheses. So we divided first, then we added 1. Next thing we're going to use the exponent of 40. So we got 1.27033, okay? So that gives us our growth rate for our compound interest. Then we take it times 1,200. So we get $1,524.41. So, again, we didn't get quite as much return on that one. Again, lower interest rate, we didn't get the interest quite as much. But again, we did get, $324 that wasn't for money just sitting there. So interest is nice. Again, sometimes you don't get a ton, but again, it does give you money for just having it sit in an account, okay? So hopefully this all made sense. If you have any questions, again, shoot me an email. I'll have a Google Hangout time for this on Mondays and Wednesdays at 11:30 to noon. So if you want a video conference with me, again, if you have any other questions, just let me know. I'll post an assignment that has a few problems over compound interest. So thank you. Bye.